Hi, my name is Amir Salari and I'm a graduate student in the Department of Earth and Planetary Sciences at Northwestern University, and I'm going to talk to you about a methodology that we developed here at Northwestern in designing and making fun, cool labs for undergraduate earth science students. Now, while watching a really cool earth science documentary or listening to really fun talks about the fun aspects of earth science, most of us have wondered whether or not we could actually do the same experiments in our classes. Can we actually do the same cutting edge experiments and demonstrations in our labs? And after probably like 3 or 4 minutes of thinking, most of us have decided whether, we don't really have enough money. We can't really buy all that sensors and equipments for our classes. And this was the motivation behind the study that we did at Northwestern. We said to ourselves, what would we need in order for those experiments to happen? We need a whole bunch of sensors, we need a whole lot of computational power, and we need the students to be comfortable using those devices. Now, after a bit of thinking, we said, why not? Why don't we use smartphones? Smartphones are really, really small computers which come in a whole bunch of sensors. Now, they come with accelerometers, they come with built-in thermometer, barometer, they come in with GPS units, and you name it. They come in with all kinds of devices. Now, in order to test this idea, we designed 3 different experiments to be done in our labs. The first one was measuring the acceleration due to gravity in a moving frame of reference. The second one was measuring the seismic wave velocity in a table. And the third one was comparing accuracy versus precision using the positioning system and the smartphones. To do the first one, we asked the students to take their smartphones into an elevator in our department and record the acceleration by putting the smartphones on the elevator's floor and running an app while the elevator was moving from the 1st floor to the 4th floor of that building. And then we asked them to extract these data using some instructions that we gave them, and then plot them and try to decipher what all those wiggles in the time series meant. Now, if you look at this plot, it's really wonderful because it has a baseline of 9.8 meters per second squared, which the students had to calibrate to sort of reason in order to find. Secondly, it's a time series with a time on the horizontal axis and the acceleration on the vertical axis. And first of all, there is a trough here in the time series, which is the decrease in the felt acceleration in the elevator while the elevator is starting off. The second part, the green part, is where the elevator reaches a constant velocity. You see that the plot plateaus. And the third part is a bump in the acceleration where the elevator is actually trying to halt. You feel an extra weight, in other words. Now, a really, really neat take-home lesson from this was that students actually got to learn about the nuts and bolts of extracting data from a device. Not just looking at a cool movie or a plot, but actually to extract those data and work with them in order to plot them. Finally, they got to interpret some of the things that they saw in those data, of course, with a bit of instructions in the lab manual. The second part of this, which is actually my favorite part because it actually needs a collaboration and a teamwork. So the students actually got to measure the velocity of the P waves in a wooden table. We made an array of our smartphones on the table, and just similar to what we do in reflection seismology. Remember, in reflection seismology, people make really long arrays with really sophisticated geophones, and then try to make explosions or pound on the ground and then make seismic shots. And using those seismic shots, they find the velocities and all kinds of seismic attributes of this stuff under their feet. Now, we did the same thing here. In this array, at one end, one person pounded on the table, and these smartphones all recorded the seismic signal, something similar to the schematic that you see here. Now, we eventually, after the experiment, asked the students to upload their data into a cloud space. Here we used the Google Drive because it was convenient. And then the students were asked to plot not only the individual time series, but then try to plot them with, next to one another. And as a result, what they came up with was something like this cross section. On the horizontal axis, you have time, and on the vertical axis, you have the distance from the pounding point, which was here at this end of the table. Now, if you look closely, this is like the 3 seismic shots that we actually put together in order to make this. But you can actually see that there's a trend in these data. There's a slope. And the slope is, well, distance over time, which is velocity. Now, you put these together and you come up with a value of about 3,500 meters per second, which is really close to the published value of velocity in wood, which is really neat. A really, really interesting take-home lesson from this experiment was that the students actually got to learn about the instrument response. They learned that different instruments treat the same signal differently. And if you look at these individual wiggles here, you can see they look, just by looking at it, you can see they're different. Now, we know that the signal was the same, and so the students tried to think about it, of course, with instructions in the lab manual that, there is something called the instrument response. They also got to look for the ways to design better arrays, which is the key point when you're doing this kind of thing in reflected seismology. The third experiment that we developed was positioning. We asked the students to go outside of the building we were having our classes here, and measure the coordinates of a point here, which was a corner of a planter that we found. And we told them to measure the coordinates using their smartphones, extract the coordinates from Google Maps, and upload those in an online document, which in this case was a spreadsheet. They just, typed in their coordinates online. And we asked them to plot these. If you look at this plot, none of these actually coincide with this yellow star, which is the geospatial reference extracted from Google Earth. And this means there is some sort of error uncertainty in the measurements. Now, we didn't stop here. We pulled the trick out of our hat and we asked them to actually identify what type of instrument they used. They used either an iPhone or Android in order to make this measurement. So the blue dots here are iPhone measurements, while the red dots are Androids. Now, just by looking at this, you can see some trends, but in order to get more sciencey and sophisticated, we told the students to actually try to make cross sections in longitude and latitude and try to see how many points actually fall within each bins of these histograms. Now here, again, it's color-coded. The reds are Androids and the blue are iPhones. And again, here is longitude and latitude directions. Now, by just looking at this plot, you can see, well, the iPhone data, while they're really, really clustered and peaked sharply, the peak is different from this really thin, narrow yellow line, which is the geospatial longitude coordinate. And this is while the Android measurements are, although they're clustered around the geospatial line, they're not peaked as the iPhones. So this will tell you probably the iPhone data are more precise but less accurate, whereas the Android data are more accurate but less precise. All of this is really fun, but probably the most important thing that we wanted the students to leave the class with was getting to work with geographic coordinates to make sense of latitude and longitude, which was the most important thing we wanted them to do. And analyzing these data in order to make conclusions. Now, this is the first step. Admittedly, we couldn't stop here. We can't stop here. These are only the 3 demonstrations that we, sort of made our case that smartphones are really nifty tools and could be useful when designing really fun labs. Now, we can either try to do the labs old-fashioned ways. Students have to walk around for many, many hours without actually, having fun scientifically, and just for one station to get free, and try to do something, textbook old way. But we also can actually let them try things in a more cutting edge of science. Our advice is on the second option. Thanks for watching.